Welcome back, everyone. In this second part of our crash course in probability theory, we will talk about random variables. The topics covered in this segment will be random variables, expectations, and random variables in finite groups. Now let's talk about random variables. So, what's a random variable? How is it defined? Well, the formal definition is given as follows. A random variable is a function x that maps from the sample space omega to some domain D. We can now associate events with this random variable. Namely, for every x in this set D, define the event ex as the set of all lowercase omega in the sample space such that x of omega equals x. And we can also write x or uppercase x equals lowercase x for this event ex. And we will call the function f of x equals probability of x equals x, which, as we just defined, is just the probability of this event ex. We'll call this the probability distribution function of the random variable x. Now, this definition of random variables as functions mapping from the probability space to some domain can be confusing to students at first. So it certainly was to me when I saw it for the first time. But essentially, random variables will fulfill the same roles as the simple probability spaces we've seen in the last lecture, like modeling the outcome of a coin toss or a dice roll. But now there can be several random variables at the same time, and there might be correlations in between them. In the last lecture, we've seen the concept of independence of events. Now let's introduce a similar concept for random variables. Let's consider two random variables, x and y, where we write x element dx and y element dy to indicate that x maps from omega to this set dx, and y maps from omega to dy. So basically the outputs or outcomes of x and y live in these sets dx or dy respectively. So we say that two such random variables x and y are independent if it holds for all lowercase x in dx, so for all possible outcomes of x, and for all y in dy, for all outcomes of y, that the events x equals x and y equals y are independent. What does that mean? Basically the joint probability distribution function of x and y, namely probability of x equals x and y equals y, is the same as the product of the probability distribution function of x and y. Now, let's look at some examples. So first, the identity function on a sample space is also a random variable, where the probability of x equals omega we just set to be the probability of omega. Next, projections can define random variables. If we have some sample space some sample space omega, which is contained in d1 times d2, then we can define two projections, x, which maps from omega to d1, and for some x comma y in omega, the output of x is just a projection on this little x. So we have x of x comma y is just x. And similarly, we can define a y. So both x and y are projections. Next, we can also do this in the reverse direction. Given two sample spaces omega 1 and omega 2, we can form a new sample space omega by taking the set product omega 1 times omega 2. Then we can define the projections as above, and those will now be independent random variables. So we say that a random variable x, which maps to some domain D, is uniform or D, or the uniform distribution on D, if for every x in D, it holds that the probability that x equals x is just 1 over D. Maybe a slightly more complicated example. Say the sum of two dice rolls. Say our sample space is omega, which is the product of the set that contains 1 through 6 with itself, and we have that probability of let's say I comma j for every ij in omega is just 1 over 36. Then we can define a random variable s by just being the projection from x comma y to x plus y. I should maybe call these two also x and y to stay with this notation, and this random variable actually models the sum of two fair dice rolls. Okay, let me maybe use the eraser. So for also for an event E, we can define a random variable, let's call it xe, which maps from the sample space omega to 0, 1, such that xe of omega is 1 if omega element E, and xe of omega equals 0 if omega is not in the set E. We call this random variable the indicator random variable of the set E, and it basically tells us if xe equals 1, this is equivalent to the event E happening, and xe equals 0 is equivalent to the event E not happening. So now that we've seen this formal definition of random variables as functions mapping from the sample space to some domain, I'm actually telling you we're actually not going to use this formal definition. We will in fact omit the function notation for random variables. Going even further, we will refrain from explicitly defining even the sample space omega. And instead, we will implicitly define omega via a set of random variables. More specifically, or phrasing the general idea, the probability space will be defined via a set of few and independent base random variables. And all other random variables of interest will depend on these deterministically. So when constructing a system that uses randomness, we won't have to keep track of the actual sample space or even care how it looks like. It will just be defined implicitly or on the fly as we introduce new random variables. And finally, some notation. If x is chosen uniformly at random from some domain D, or if x is a uniformly distributed random variable on some domain D, we will use this notation that x is assigned with a underscore dollar from D. So we will use this notation to denote that x is chosen uniformly random from D, instead of going through this function notation and actually defining the probability distribution function of x. Okay. Now let's look at a few examples. So let x1 to xn be independent random variables such that each xi is uniform on 0, 1. So for this, we can, of course, with this new notation, equivalently write x chosen uniformly random with this dollar from 0, 1. So we will say that x are IID uniform on 0, 1 for short, or x1 to xn are independent and identically distributed uniform on 0, 1. So if we take the entire vector x1 to xn, then this vector is distributed uniformly random on 0, 1 to the n. How can we see this? Well, we say that x1 to xn are, let's maybe do this do this over here on this side. x1 to xn are independent, so the probability that uppercase x1 to xn equals lowercase x1 to xn is just by independence the product from I equals 1 to n probability uppercase xi equals lowercase xi, but we know each of them is just 1/2. So this is 1 over 2 to the n, which is just the size of, or 1 over the size of this set, 0, 1 to the n. There's 2 to the n elements in 0, 1 to the n. So we get that x is, or uppercase x is in fact the uniform distribution on 0, 1 to the n. Now we can perform a different operation on these x1 to xn. For instance, take the sum. So let's define y as the sum of x1 to xn. Then this y follows a distribution which we call the Bernoulli distribution. And down here I gave you a plot of the function probability y equals let's say lowercase y, where lowercase y ranges from 0 to 16, and of course my n here, n in this example, is also 16. So this is obviously a random variable which is not uniformly distributed, but which is concentrated around the central value 8. So the random variable y defined in the last example was just a simple function of the base random variables x1 to xn. In general, we say that a random variable z is sampleable if there exists an efficient algorithm M such that z is just M of x1 to xn, where the x1 to xn are IID uniform on 0, 1. Such an algorithm M we call a sampling algorithm. And the x1 to xn are called the random coins, or just coins of the sampling algorithm M. So here we see this idea that all variables are defined depending on some base random variables in action. So the coins x1 to xn are our base random variables, and this variable z is just a deterministic function of these coins. So now we turn to the important case of real valued random variables. And we call a random variable x real valued if it is supported on the real numbers, or if the values that x assumes are a subset of the real numbers. And we call the set x of omega, or the set of possible values that x assumes, the support of x. And we note that since omega is finite, the support of x will also be finite. A basic characteristic of a random variable is its expectation. That means it's a quantity that doesn't completely describe the random variable, but tells us a lot of important information about it. The expectation of a random variable is defined as the weighted average of the values it assumes, where the weights or the weight for the element x is just a probability that the random variable x outputs the value x. Let's study this for a moment at with an example that we've already seen. Let's take the random variable x, which outputs 0 with probability 1/2 and 1 with probability 1/2. This is x is an unbiased coin. So in this case, the support of x is just the set 0, 1. How do we compute the expectation? Well, the expectation of x is 0 times probability that we get 0, that's 1/2, plus 1 times probability that we get 1, which is exactly 1/2. So for binary random variables, the expectation always has a very simple form, even if we didn't have an unbiased coin here. But even for the case of a biased coin, where we say had probability of 1 is p, probability of 0 is 1 minus p. In this case, the expectation of x is 0 times 1 minus p plus 1 times p, which is p. The expectation of a real valued random variable x is just a single real number, but it encodes actually a lot of useful information about this random variable. And one way this can be exploited is by using a property of the expectation, which is called the linearity of expectation. So expectations are some characteristic of random variables, or as I just called it, some useful value. And they're in fact a powerful tool to analyze random variables that we've constructed from other random variables. So what does linearity of expectation state? Well, let x and y be two real-valued random variables, and let alpha in R be a constant. Then it holds that the expectation of alpha times x is alpha times the expectation of x. Second, the expectation of x plus y is expectation of x plus expectation of y. And an important point here is that we haven't made any assumption on x and y such as if they're independent. In fact, we won't require that x and y are independent. This property, linearity of expectation, will hold for random variables x and y that are arbitrarily dependent. So now let's look at the proof. And the proof of the first item is maybe a little bit tricky. So we're gonna use the following observation. For a random variable x, the expectation is defined as the sum of all lowercase x in support of x, x times probability of x equals x. But now we observe that this probability distribution function is zero outside the support of x. So if the support of x is contained in a set S, we can write this as well as x element S, x times probability of x equals x, as the x outside the support of x have a probability of 0 anyway. Okay, so now let S be some finite set that's large enough to contain support of x, support of y, and support of x plus y, all in this set S. We could take the union, but in a moment we need this set S to still be a bit bigger. So let's now look at the expectation of x plus y, and this is just plugging in the definition, going over all, let's say, z in the support of x plus y, z times probability of x plus y equals z. Okay, so the first thing that we're going to do now is we're going to rewrite this probability of x plus y equals z. Let's do that now. Probability of x plus y equals z can be rewritten as the sum of overall y in the support of y probability of x plus y equals z and y equals y. Why can we do this? Well, we have just used the law of total probability. The events y equals y, going over all lowercase y, are a partition of the sample space, and therefore we can use the law of total probability. Now we go a small step further. Maybe let's first write this here. This is sum over all. Let's maybe start with y element support of y, some z element support of x plus y, z times probability of, before I continue here, let's just realize that this, if we already know that the event y equals y holds, then x plus y equals z can be rewritten as x equals z minus lowercase y. Okay, now that we're here, let's write this here. X equals z minus lowercase y and y equals y. So now that we're here, let's perform a variable substitution. Namely, we substitute z with x plus y. So we just choose an x coming from a domain large enough such that we reach all possible values of z in the support of x and y if we go over all these x. So we can rewrite this as y in the support of y, but now I'm as discussed up here, replacing the support with the set S. I'm going over all y in this set S, and now I'm also going over x in this set S, and z is now just x plus y. Have x plus y times probability x equals x, y equals y. And I have already a much nicer form of this expectation. And now it'll turn out I'll just have to apply the law of total probability twice more, and we will be done. So let's first use distributivity and rewrite this as sum over all y. I'll just drop the domain S. Sum over all lowercase x. X times probability x equals x, y equals y, plus sum y and x, y times probability x equals x and y equals y. So let's arrange these sums here, or rearrange these sums here. The first one can be written as, let's just make these sums switch places. Here we can write this as some y element. Let's just say we're going over y. Y times probability x equals x, y equals y, and here we have sum over all y, y times sum over all x, probability x equals x and y equals y. So if we now look at this term and this term in here, sorry, this y here is too much. We don't need a y. We don't need this y here. This term here, by applying again the law of total probability, is just probability x equals x, because the y equals y are just a partition of the entire probability space. And here the same thing, but with roles reversed. This is just probability y equals y. Finally, maybe I'm gonna continue down here. This is just, well, probability over all x, x times probability x equals x, plus y, sum over all y, y times probability y equals y. And this is just the expectation of x plus expectation of y. So a little bit tedious, but in the end it boiled down to applying the law of total probability 3 times. Okay, so now let's prove the second property. And this one will be, in fact, a lot easier. So what's the expectation of alpha times x? Well, let's write it down. Let's again go over all z in the support of alpha times x, and this will be z times probability alpha times x equals z. And now again, we just run a or perform a variable substitution. Let's just assume alpha is non-zero. If alpha is 0, then the statement is trivial, because then alpha times x is 0, and the expectation of the constant 0 random variable is just again 0. So let's assume alpha is non-zero, and now let's just perform a substitution and say z is just, let's say, alpha times another counting variable z prime. So substitute. So we can rewrite this sum as going over all z prime. Here we have alpha times z prime. And what about this probability? Well, we have alpha times x equals alpha times z prime. Well, this alpha cancels out. This is just probability of x equals z prime. So altogether, this makes alpha times sum over c prime times probability x equals z prime, which is just alpha times expectation of x. And this concludes this proof. So how can we use linearity of expectation? Let's just look at a quick example. Let x1 to xn be independently distributed random variables on 0, 1, such that for all I, it holds that the probability that xi equals 1 is p for a constant p between 0 and 1. So each xi is in fact a biased coin, as we've defined in the last lecture. So now what we're interested in is the expectation of the sum of xi, and we call this y. So what is the expectation of y? Which is the expectation of x1 plus and so forth until xn. Well, the first thing that we can do is apply linearity of expectation, and we get that this is just the sum of the individual expectations. So it's a sum of x1 plus and so forth xn. So we already know that the for each I we have a probability of xi equals 1 is p, and that is already enough to compute the expectation. We know that probability xi equals 0 is 1 minus p, but that's not even needed. So what's the expectation of xi? And here we can just use the definition. This is basically, well, we sum over 0, 1, and we have b times probability xi equals b. Well, for b equals 0, this is just 0 times something, which is 0. So what's left is this is actually 1 times probability xi equals 1, which is exactly p. So we can finish computing the expectation up here. This is just p plus and so forth plus p, the whole thing n times, which makes this n times p. And that's the expectation of the sum of these biased coins. We will now take a quick detour to algebra and talk about finite groups. So how are groups defined in algebra? Well, a set G together with a binary operation is called a group if the following conditions are met. First, we require associativity. That is, for all f, g, and h in the group, it holds that f times g times h is the same as f times g times h. Second, we require the existence of an identity element. That is, there exists a special element E in the group such that for all G in G, it holds that E times G is the same as G times E is G. And third, we require that every element in the group has an inverse. That is, an element G prime such that G times G prime equals E. And it is not hard to establish from these three requirements that identity elements are unique. That is, there's just a single identity element in each group. And inverses are unique for every G in the group. That is, every G just has one element, G prime, which we typically call G inverse, such that G times G inverse is E. Now, for some little extra terminology, we say that a group is commutative or also abelian if it holds for all G and H in the group that G times H is the same as H times G. And we say a group is finite if G is finite as a set. Now let's briefly look at some example groups. The first are just integers under addition. So here the set G is just the integers, the group operation is addition, the neutral element or identity element is 0, and to form inverses you just take negatives. This is an infinite group, so this is not an example of a finite group. The second examples are just modular integers under addition. So here our group is Z mod MZ, which is typically represented by the integers between 0 and m-1. The group operation is addition mod m, the neutral element is 0, and inverses are again negative numbers mod m. And this, of course, is a finite group, as here the set G consists of just m elements. Let's erase this maybe. So the third example are the non-zero rational integers under multiplication. So here our set G are just the rationals without 0, and the group operation is multiplication. Now the identity element in this group is 1, and forming inverses are just multiplicative inverses. And again, this is not a finite group. By the way, all these groups here that we've seen are also commutative. The third example is just a special case of the first example when we, the second example, where we set the modulus m to be 2. So the binary set under XOR is also a group where the identity element is 0, and taking inverses, well, it's you do nothing. The inverse of 0 is 0, and the inverse of 1 is 1. The last example are binary vectors under XOR. So here our set G are all binary strings of length n, and the group operation is bitwise XOR. And again, the identity element is just the all 0 string, whereas inverses are formed by, or an inverse of an element A is just the element A itself. Finally, let's talk about random variables in groups. So now let U be a uniformly distributed random variable in a finite group G. That is, it holds for all group elements G in G that the probability that U outputs G is 1 over size of the group. Now fix a group element G, and the first thing I'm asking, what is the probability distribution of U times Z? So what is probability that U times Z equals X? Now, we know that in groups there are inverses, and therefore this event up here is identical to the event U equals X times Z inverse. Now we know that U is a uniform distribution, so this is just 1 over G. Good. So next, we want to ask what is the distribution of U times Z if Z is any random variable which is independent of U. So now it's not any fixed constant anymore, now it's a random variable. And to analyze this distribution, we can just use the law of total probability. Let's do that. So probability U times Z equals X is just, well, let's sum over all Z in the support of Z. probability that u times z equals x and z equals lowercase z. But now, again, we can rewrite that just as above. Here, we know that z equals z, so this is the same as u equals x times z inverse and z equals z. Furthermore, we know that u and z are independent. That means we can write this probability as u equals x times z inverse times probability z equals z. All right, so finishing this up, we can write the entire probability as probability u equals, let's maybe go one step back. And first observe that since u is a uniform distribution, this is 1 over group size. Consequently, the entire thing becomes 1 over group size times some z in support of z, probability z equals z. And this is just 1, so the overall thing is 1 over group size. And we obtain that u times z is again a uniform distribution. So when we take any random variable z and multiply it with a uniformly random group element u, which is independent of z, we get a uniform distribution. In particular, if we look at a specific group, say G is again the binary group with group operation XOR. If U is a uniformly random bit, then U XOR Z is again uniformly distributed, uniformly random, as long as Z is independent of X. Independent of U. So now it's time for the summary. We've seen that random variables are the right way to define and work with probability spaces. In computer science, we usually define all variables depending on some uniform and independent base variables. For real-valued random variables, we can compute a quantity called expectation. The expectation is linear. And finally, we've seen that XORing uniformly random and independent, or XORing a uniformly random and independent random variable onto something else results again in a uniform distribution. All right. So now that we've finished this introduction on probability theory, here's a tweet I recently ran across in my feed. Well, how would you answer? Or maybe how should you answer as a computer scientist? That's it for today. Thanks and goodbye.